Hi everyone, thanks for coming to my talk. So over the years, we have been talking to many users about machine learning. This includes our colleagues in other departments, such as astronomy, biology, and social science, and also users in both public and private sectors. What's very clear from talking to and working with all of these users is that almost everyone is very excited about the potential revolution that could be enabled by machine learning. However, when it comes to building a machine learning application all by themselves, it's a completely different story. Because alongside all this excitement, we see new machine learning methods and models being developed almost every single day. And many machine learning systems are also developed to form an ecosystem that's increasingly complex and hard to navigate. We believe that to unleash the full potential of machine learning to society, we need to make sure that all those users who are building machine learning applications are actually those people who are familiar and deeply cares about a certain domain, even though they have never been through the formal training of machine learning and computer science. However, the increasing complexity of machine learning ecosystem is creating a gap between these users and the machine learning technology. And we are not alone in observing this. There have been a great collection of very inspiring work done by our community to try to bridge this gap. In this talk, I will share with you some of the work that we have been doing about raising the level of abstractions of building machine learning applications. Without going into the technical details, we will focus more on the usability challenges that we hope to solve and the lifecycle management system that we were trying to build called EaseML. So when we first look at usability in 2016, we thought that the speed and degree of automation of a machine learning system was all we need. Well, both of them are actually very, very important. It took us an embarrassing long amount of time to realize that these two aspects are not really the full picture. In fact, even with a machine learning system that's very fast and fully automated, we see struggles from our user in using them. And all these struggles happen in both the development phase and also the deployment and the maintenance phase. The first struggle that we see is what we call unrealistic expectation. It happens when a user have a very high expectation on the quality of a machine learning model, but do not really have the right data to support it. We see many users start very expensive AutoML runs on a dataset that's way too noisy to meet their quality expectation in the first place. And they often get very frustrated after spending all these resources but cannot reach their goal. The second struggle is what we call premature quality optimization. It happens when a user tries to improve the quality of a machine learning model during development. To improve a machine learning model, the user can do a whole bunch of things, such as data cleaning, data labeling, and acquisition. Unfortunately, we often see users get confused on what the right thing to do is among this great collection of choices. And sometimes we see users waste effort doing something that will not give them a significant improvement of the model quality. And as you can imagine, the user's lives are not getting any easier during the deployment and maintenance. The user constantly face new machine learning technologies that they hope to integrate into their applications. But on the other hand, they often worry about whether the improvement they get in this continuous development process is overfitting or not. They also need to worry about the risk of unknown data distribution drifting. If you look at all of these struggles, they are centered around the interaction between a user and the AutoML system. And many of them will not get any better by simply making a machine learning system faster and more automatic. Inspired by all these struggles that we see from our user, we believe that what is missing is a set of principles enforced by a collection of tools to guide the user through the full life cycle of machine learning development and deployment. So EaseML is our first trial in doing this, which provides a collection of tools that together defines an end-to-end machine learning process. While building many of those tools are actually technically engaging on their own, in this talk, let me show you the process If you are interested in how each of these tools work, you can find more details on our EaseML website. EaseML is integrated with the Jupyter Notebook, which is a very familiar environment to many users. The very first step is to load the dataset. So here, EaseML distinguishes 4 different types of datasets. All have the same data schema, but different freshness and quality. We call them the training side, the validation side, the testing side, and the production side. The production side is the freshest one, coming directly from the production, which does not have labels. But testing and the validation side are labeled datasets, but they are less fresh compared with the production side. Whereas the training side could come from a very different distribution because of weak supervision, and they may contain both labeled and unlabeled data examples. Once these datasets are loaded into the system, the first component of EaseML is a tool that we call Data Magic. Data Magic automatically injects uncertainties into the data and output a probabilistic database that all downstream EaseML components are going to work with. These uncertainties can come from different sources. For example, running existing data cleaning tools can give you alternative values for features. Running weak supervision tools can give you alternative values for labels. Data augmentation and missing values in both features and labels can also introduce uncertainty. One key design decision in EaseML is to model all these different sources of uncertainties in a single unified framework. And we treat improving the quality of a machine learning model as a process of eliminating different parts of uncertainty. Once the data is loaded, the user then loads a collection of old models. We call this the model pool. We assume that all the models in this model pool are candidates for final deployment. The goal of the user is really try to develop a new model that is better than all these old models and add this new model into the model pool. Once the dataset and model pool are loaded into the system, the user now starts their EaseML journey. One primitive that we introduce is a command called what next. When the user issues this command, the system provides suggestions on what it thinks the user should do next. Some of these suggestions are actually pretty standard. For example, here, the system may ask the user to identify which column should serve as a label. The user can simply follow this instruction and call what next again. The first non-trivial step of the EaseML process is what we call feasibility study, which is enabled by a tool that we call Snoopy. This step takes as input a quality expectation from the user. For example, we hope the accuracy to be higher than 80% at the end. It then tries to estimate whether this goal is really feasible or not with an estimator of the best achievable accuracy given the current dataset, without running an expensive AutoML system. If Snoopy believes that such a quality target is not really realistic, it will then bring the user into the quality engineering phase. So in this phase, the system will suggest some operations that users should do to improve their dataset. For example, here the system believes the user could do both data cleaning and data acquisition, but it also believes that the user should do data cleaning before data acquisition. For both data cleaning and data acquisition, the system will actually suggest some examples that it believes the user should look at in order to maximize the final model accuracy. The goal here is to give users the guideline to make sure they can focus their effort on where it matters. And after multiple of these iterations of data cleaning, acquisition, and feasibility study, it then comes the time that we can fire up our AutoML system. And during AutoML, what the system is going to do is to automatically try a different set of combinations of models, features, and hyperparameters, and return the best model to the user. The user can then pick the best model as candidate for deployment. Now let's come to the testing phase. EaseML provides two testing functionalities. The first one is try to enable a CI/CD workflow for machine learning on the validation side. The input is a new machine learning model and the old model in the model pool, together with a condition such as the new model should be better than the old model by at least 1 point, together with a confidence interval and the probability for such condition to hold. The CI component will then return a Boolean signal indicating whether this condition holds for this new model, providing strong overfitting guarantee even when we are reusing the same validation set multiple times. If our new model passes the CI setup, we can then add it to our model pool. The next phase is what we call model picker, which try to pick the best model given unlabeled production set. The goal is to minimize the labeling effort to pick the best model by asking the user to label only a carefully selected subset of examples. When this step is done, the user finishes one pass of the EaseML process. I will then start to further improve the quality via another pass of data cleaning, acquisition, and labeling suggested by the EaseML system. This is the default process defined by EaseML, which tries to help the user to optimize for expected quality improvement over time. It is designed to be flexible enough such that the user can actually skip some of the steps. What you see is just the very beginning of our journey. Most of these EaseML components require us to solve some new technical challenges, and it took us years until today to build the first prototype for each of them. During this process, we also found a lot of technical limitations in each of these components that definitely need more work from us and a lot of help from you. We are very excited to hear your feedback and discuss technical details offline. Thank you very much for your attention.